as I explained before in the outcome, the dream. So in test cases with 3 products, we begin to have difficulty. Our algorithm begin to have difficulty to perform as good as in the 1 or 2 product types. So we can see that the execution time is getting longer. So here in the 32 hoppers, in several instances, we have this consistent high execution time.
And Teddy, you have to say these are milliseconds. Okay.
Oh, these are in milliseconds,
Yeah.
but the execution time is in milliseconds. But for the typical typing speed, we have between 120 to 200 winging per minute, or it is about 300 to 500 milliseconds. So for example, if we have 183 milliseconds here, so for the taking time 300, it is more than 50% of the process. So clearly this is not good enough for the actual or the real world application. So based on this initial result, we have a summary. So for all of the test cases, Cplex obtained optimum, and Aku obtained 97.3% optimum in all of the test cases. For the 16 hoppers, we have in 1 and 2 product, there is no problem. In the 3 product, we have problem in quality. So this problem is not related to the performance of the algorithm. It is related, or it is caused by the quality of the instance. So we have for all of the instances, we have optimum solution, but the value of the optimum solution is not good enough in the viewpoint of real world production. So for the 32 offers, we don't have any problem with 1 or 2 product type, but we do have problem in 3 product type. So the problem exists in quality and execution time. So this is the important one, because it suggests that there are rooms for improvement for the algorithm to be used in the real world application of MWM. So we identify that there are two causes of these anomalies. So the first one is the quality of the instance, and the second one, it is because the configuration or the winging configuration provide complex or hard challenge for the optimization algorithm. So for your information, that all of the result is obtained by using the cluster, in our institute. Of course, this is not a realistic test, because the one used in real world or in industry is like this. The specification is like this. So the processor speed is very, very low, and the storage and the RAM capacity also low. So based on this, we do our ongoing work by doing several things. So the first one, we do physical experiment to obtain instances data that can better represent real world MWM operation and design. And we will, in our initial work, we test the algorithm one winging at a time. So in the next work, we will test the algorithm in scenarios consisting several or many winging process in multiple winging batches. So other than that, we will do tests on a resource constrained microcontroller, like the one used in the real world application. So this is to evaluate the robustness and efficiency of algorithms that we will develop. So this is the physical experiment that we do. So we have several variations. The first one is the variation of the cone angle. We have 90, 110, 130, 140, and 160. And the second one is the product shape. So this is to represent different types of product. In our initial work, we only use synthetic data. We just give label this one product 1, product 2, and product 3. And in this experiment, we can have different product shape here that represent product 1, product 2, product 3, product 4. And the third variation is the product layout. So we have loose and tight. And this is to represent the real operation of MWM. So all of this we do with the intention to provide instances that can be used realistically to evaluate the robustness of the algorithm. So this is to represent the design of the MWM. This is to represent the variability of product, and this is to represent the variation in production or operation of the MWM. So this is the machine that we use for physical experiment, and this is how it is operated. So we have not installed a funnel here, so we can see that the distribution is most of the product is distributed in the front side of the hopper. And this one, we install a funnel here, and the distribution is getting better. So we have several products distributed in the back side of the hopper. So this is the result that we have from our physical experiment. So this is this is the distribution of product in 16 hopper. This is the weight. The vertical axis is the weight, and the horizontal axis is the hopper identity. We have four graphs representing 4 shapes. So this is for plate, cylinder, cube, and block, and this is the distribution.
Teddy, one question. What are the different colors of the dots?
So we have 20 repetition. So for each shape, for each variation, combination of variation, we do 20 weighting. So this is the result between the different shapes. We have this different distribution. This is for loose layout, and the second in this next slide is for tight layout for different shapes. And this is the result if we compare this product distribution in different cone angle. So for 90 degree, 110, 130, 140, and 160. You can see here that we have different variation. So in 90 degree, we have this small variation of product, and 130 we have larger, 140 we have even larger, and in 160 this very bad because some of the hopper sometimes didn't get any product in it. So this is 0. For 0, it means that there are no product accepted by the hopper. So by using this physical data, we can generate, or we can compile instances that with similar variation with our initial work. So in our initial work, we have 16 and 32 hopper. In this physical experiment, we only have hopper with 16. We have 16 hoppers here. So in this video, we have not add a divider here. So in later experiment, we had divider here. So the number of hopper is 16. So our physical experiment has 16 hopper, but we know from our initial work that the algorithm didn't have any difficulty to solve 16 hopper. In test cases with 16 hopper, the algorithm doesn't have any problem. We have good execution time. So if we really want to test the algorithm to the maximum of its capability, we should test it on 32 hoppers and 3 product type, at least this configuration. Our physical experiment only use 16 hopper, but we can use the experiment data to generate scenario of weaving for 32 hoppers by using this configuration that already exists in real-world application. So we have 3 different MWM configuration design. The first one is single layer. The second one and the third one is double layer. So in the first one we have series layer of feeding hopper, and then it is the weaving hopper. For the double layer configuration, there is one more layer here. It is called the booster hopper. This is the booster hopper. So double layer MWM has 2 types. The first one is the parallel type. The second one is diagonal type. For the parallel type, we have available option. We can choose booster hopper 1, 2, and 3 in this illustration, or we can choose booster 1, 2, and 3, and also we can also choose booster 1 plus weaving hopper 1, booster 2 plus weaving hopper 2, and booster 3 plus weaving hopper 3. So in this configuration, we can have double number of options available. In this case, in this MWM type, we also have the double number of options if compared with the single layer MWM. So in this configuration, weaving hopper 1 can directly supply its product in the discharge chute, or it can supply to the booster hopper 1. So we can, in this case, we can select every hopper available. So all of hopper in booster hopper and all of hopper in weaving hopper can be chosen. So in this case, even though the number of radial hopper in radial direction is 16, we have 32 hopper available to be chosen by the optimization algorithm. So using this design, using this design, we can have a scenario where we can generate instances that has 32 hoppers. So we hope we can, by using this, we can test the algorithm to its maximum performance. So as I said, even though as I already explained before, we only have problem in 32 hoppers and 3 products. We don't have any problem for 32 hoppers and on 1 or 2 products. So for generating instances where we use configuration of 32 hoppers and more than 2 products, we will use this strategy. So, for example, we have here for hopper 1 to 4, we will use product type 1. Hopper 4 to 8, we use product type 2. And 9 to 12, we have product type 3, and 13 to 16, we have product type 4. So this is what we will use for generating instance. And this the example of the instance. So we have here that in the first row, it is not displayed fully. We have here in the first column is the ID of the weighing process, and this second column is the cone angle. This one is the product set, and this one maybe I forgot the layout, and this one is the repetition. So we have 20 repetition of each configuration, and the remaining of the column consists of the width of the product in each hopper. So we have 16 column go to the back. So we can ask the program to combine. So we have this file for all of the data, and then for the execution we can ask the program to combine to access different scenarios with different configuration of product 1, 2, 3, and 4. And for the metric, for the performance metrics, and in our test, as usual, as the standard performance metrics, we will measure or we compare the accuracy and precision of the optimization algorithm, and then the execution time. And we have these two metrics that we have not used in our algorithm benchmark, which is the memory utilization and system stability and robustness. So it will be used to evaluate the robustness of the algorithm. And for the conclusion, our initial study has shown that ACO can perform very well, but in certain cases it needs more execution time, which is not enough for real-world application. So we need more robust and efficient algorithm to tackle MWM, especially for complex configuration. And then our ongoing work will focus on developing this algorithm and test them in a resource-constrained microcontroller typically used in MWM. And my hypothesis is that if we can successfully develop these algorithms, we can use this algorithm to as leverage for simple and low-cost MWMs to compete against more complex ones. Yes, and this is concludes my presentation. So now I'm open for discussion or maybe suggestion.
Okay.
Thank you. Is there any questions?
Yeah,
Can you look?
yeah. I don't understand why the difference they use Ziplet and ACO. Why the advantage of using ACO for the hardware limitation? Is because they use more or less memory, or
Yes.
yeah,
Exactly.
okay.
So,
Yeah.
so
Because in the result, Ziplet and ACO is very similar, no? In the table,
yes.
only different is the
Yes.
millisecond.
And maybe because the instance not which maybe the instance is very easy for
Okay.
algorithm.
Okay.
But we cannot use Cplex or ACO for real world application in this machine, because as you can see the specification of this machine,
Yeah.
and this microcontroller we use in this machine. So our ACO algorithm, the size of ACO executable or compilation is 60. So for this, of course, not enough. So this is also limited. This one is a general purpose microcontroller. I think it's quite decent.
Yeah.
So it has better specification.
So in this hardware, ACO is work well
No, we test ACO and Cplex in here.
Okay.
So for the Cplex, the file size, the compilation size is
Yeah.
32 megabyte.
Okay.
Yeah.
So it's not, it cannot be used.
Okay.
So if the memory is a problem in the real world settings, why you're using like a population-based algorithm rather than like a trajectory or local search?
Yes,
Yeah.
exactly. That is one of the. I think why we use ACO and the Cplex, we use it only as a preliminary tool to probe the characteristic of the problem.
Yeah, because for this hardware, probably you need a very simple heuristic.
Yes.
Yeah.
I don't know, maybe A-star kind of.
Yeah. We were thinking about iterated local search, no?
Yeah.
Yeah,
Something which just works on a neighborhood, one solution,
one solution.
and changing it. No? But I think we also need to compare to what they use, the complete enumeration.
Complete enumeration.
We have to know how long this takes.
Yes.
I think this is something essential.
Yeah. So I calculate the number of combination.
And yeah, here for example, I have a question about
Yes.
the K, the problem.
Which one? This one.
K. So you said that this is the expected number
of hopper to
Oh,
be chosen.
Is it something like a hard constraint? Is just
No. So
the algorithm doesn't force to be
no.
selected.
No.
Okay.
So if it needs more hopper, it will select more hopper. So if the target width is already passed, then it stops. It doesn't have to. Oh, this is the allocation of hopper allocated for each product type. So for 32, each product type has 8 hopper to be allocated for each product type. So it doesn't have to select each every hopper or 8 hopper to obtain the result.
But if you have 32 hoppers,
Yes.
and we have 3 products,
Yes.
how can K be 7? I mean, don't you have to...
Other product have more hopper to be allocated.
But then, no, I still don't understand it. So if K is 7,
Yes.
this means one of the products has 7 hoppers,
Yes. two of the product have 7 and one
Ah,
have more.
okay, okay. Okay, okay.
Yes.
I have a question about this data instance generation, okay?
Yes.
I've seen that, I mean, all your different product types, which are like the cube or the cylinder,
Yes.
is all wood.
Yes.
Have you thought about using some other material apart from wood and repeating it?
So in Indonesia, we have wood very cheap
Mm.
compared to plastic or metal.
Mm.
So one of the reasons is that. But if we use food, maybe food we don't have, we will not have good consistency between each experiment, because the food can change quickly.
Mm. Yeah, but I don't know what could be a cheap material, just to have two different materials. Maybe some poly, I don't know, what is this called? What you use for isolation, for example. You know? Like what which you can cut easily.
Yeah, the white.
How do you call it?
It will fly away.
You fly away. It's too light, eh?
Yeah.
Too light, okay. So you have thought about different material, but
Yes.
it's not easy.
I think the most suitable is
Is wood.
Yes.
Yeah, okay.
Did you make the experiment, the physical experiment for each type of product, or did you mix them also?
No, we don't mix them.
You didn't mix.
Because if you mix them, we cannot have control of
Yeah.
the proportion.
Mhm.
Mm.
We have.
But there's another idea. If you want to have two different materials, you can have a wood which weighs a lot, a dense wood, and the light wood.
Yes.
Yeah.
The dense wood maybe price a little bit more
Ah,
pricey.
okay.
So I think this is the most reasonable, the most feasible.
Ah.
I think even if we only use one material, we have a very diverse
Mhm.
result.
Mm.
Yes.
Okay. Yeah, I think the essential thing is really to implement an algorithm on one of these microcontrollers and to compare it to a complete enumeration, what they use in industry. And if we can show them that then our algorithm is better, then this would be good. Yeah.
So I calculate the number of
Yeah.
solutions, and here we have only 1,000 or 50,000
Mm.
combination, and the number begin to explode here.
Yeah.
And if we only use variation of number opera, we don't have enough number of option. But if we add this one, we will have a very large, maybe I think it's around 3 million
Okay.
something.
So this is where complete enumeration could be
Yes.
too slow. Then.
Yes.
Yeah. Okay. Mhm.
Okay, maybe some other question.
What was the stopping condition on coming?
Stopping condition is time. So for our execution, we give limit 1 second. So this is the best result that they produce within 1 second. Okay, maybe other question.
Question about you said that here, for example, the optimal solutions gave like a lot of product to the
People.
client
Yes.
that you cannot solve it with your constraints. But are you planning on changing the constraints of
Yes,
sort of
yes.
this?
I think that's why I need to test the instances from real-world application. Thus, real-world application can give result like this. Because in this one, we have very small standard deviation. I don't know why it can have things like this. So all of this is optimum. So it means that there is nothing wrong with the algorithm. What makes the result like this is the option that is available in the instances.
But then, Teddy, I mean, these are instances generated by us, no?
Yes.
We don't know if this combination happens really in some real life case. No?
Yes.
We don't know.
Yeah, that's why what I was asking that maybe also in these real life cases it happens also.
Maybe.
And I don't know if you can change anything about the
It could be.
problem.
Yeah.
To solve that.
Then you have to change something with the machine.
With the product,
Yeah, with the product.
maybe having smaller pieces or something. Or
Yes. So the other thing that we will do in our experiment is that we will generate test case consists of multiple viewing process. So this is obtained in only one viewing. So we will see how we can mitigate something like this. So we still have several batches to come. How can we minimize things like this to happen? Okay. Any other question?
okay, if not, thanks, Teddy, again. Okay.
Thank you very much for attending this talk.